So to find the area under this curve from of 2e to the 2x, we've got the 2e to the 2x curve from 0 to 3, so I've shaded that area. So to do this, we're again going to find the antiderivative. So we end up with 2e to the 2x over 2, and we're going to find the displacement on that antiderivative function from 0 to 3. So I'm just going to simplify that. That's going to be e to the 2x from 0 to 3. That area works out to be e to the 6 minus e to the 0, which is 1, or e to the 6 minus 1. Okay, so that represents my area underneath that curve, and that's going to work out to be about 402.4 units squared. Okay, so that curve actually goes up very quickly. That's why that area is so big. Okay, so the idea then is that the fundamental theorem, the one part of the fundamental theorem of calculus states that the displacement on the antiderivative function is the same as the area underneath the curve between any 2 points. So putting this into here, we have our secant squared function. So if I just sketch a quick graph of this, secant squared is going to be some graph that looks something like that. And that's going to be at y equals 2. So the area from 0 to 0.5, let's say 0.5 is somewhere around here, and we want that area, we're going to use the antiderivative function. So the area is going to be found using the antiderivative function. So this is going to be 2 tan x. Derivative of tan is secant squared. So the antiderivative is tan. We need to divide by that coefficient of 2. And then we have our bounds from 0 to 0.5. Okay, so we end up with the tan x, tan to the 2x. Oh, let me make that. I made a mistake there. That's going to be tan 2x. So we have tan 2x from 0 to 0.5. So plugging that into my tan, I get tan of 1 minus tan of 0. And I can plug that into my calculator and I get the tan of 0 is 0. So tan 1 is 1.557. So we're going to get the area underneath that curve is 1.557 units squared.